Hydrogen isotope effect on self-organized electron internal transport barrier, criticality, and role of radial electric field in toroidal plasma. Self-organized structure formation in magnetically confined plasma is one of the most attractive subjects in modern experimental physics. Non-equilibrium media are known to often exhibit phenomena that cannot be predicted by superposition of linear series. One representative example of such phenomena is the hydrogen isotope effect in fusion plasmas, where the larger the mass of the hydrogen isotope flow is, the better the plasma confinement becomes, contrary to what simple scaling models anticipate. In this article, threshold condition of a plasma structure formation. In a magnetically confined plasma is one of the most attractive subjects in modern experimental physics. Non-equilibrium media are known to often exhibit phenomena that cannot be predicted by superposition of linear series. One representative example of such phenomena is the hydrogen isotope effect in fusion plasmas, where the larger the mass of the hydrogen isotope flow is, the better the plasma confinement becomes, contrary to what simple scaling models anticipate. In this article, threshold condition of a plasma structure formation is shown to have a strong hydrogen isotope effect. To investigate the underlying mechanism of this isotope effect, the electrostatic potential is directly measured by a heavy ion beam probe. It is elucidated that the core electrostatic potential transition occurs with less input power, more normalized by plasma density in plasmas with larger isotope mass across the structure formation. This observation is suggestive of the isotope effect in the radial electric field structure formation. A long-standing open question in the magnetically confined plasma study is the hydrogen isotope effect. The heavier the flow particles are, the better the confinement becomes, contrary to what simple scaling models anticipate. Here, the simple scaling models refer to EZ, bond, or gyrobond theory, where diffusion of plasmas produced with heavier hydrogen isotope is expected to be larger due to their large diffusion step size. The hydrogen isotope effect has been classically assessed by means of the global confinement time scaling or the local diffusivity. When evaluating such parameters, it is usually inevitable to rely on specific assumptions in heating profile calculation or transport models, which can be sources of uncertainty. Moreover, the hydrogen isotope effect in global or local transport coefficients is not always distinct but can be marginal, particularly in stellar layers. Therefore, a large-scale statistics is necessary for drawing a conclusive trend, which can hamper interpretation on detailed underlying process. The hydrogen isotope effect is also known to be evident in the edge transport barriers or the international transport barriers, where the threshold condition for the transition is eased in plasmas with larger ion mass. The transport barrier criticality can be qualitatively defined without any model's assumption. Therefore, an experiment-driven discussion for unveiling the underlying physics of the hydrogen isotope effect is possible. Furthermore, as the future, their mononuclear fusion plants is currently planned to be operated with the tritium-deuterium mixture flow and with transport barriers. Understanding of the background mechanism of the hydrogen isotope effect is important for projecting the reactor plasma performance. When the transport barriers emerge, a localized radial electric field structure is spontaneously formed by the quasi-neutral plasma, which is believed to suppress the anomalous turbulent transport. Direct measurement of the radial electric field in systematic isotope experiment is therefore a key factor for resolving this issue, but has been challenging for a long time. In this article, the hydrogen isotope effect on the ITB criticality in the Large Helical Device (LHD) stellarator is elaborated, focusing upon the ITB in the electron temperature profile, the so-called electron ITB, the threshold. Value in the input power normalized by plasma density for triggering the electron ITB is found to be lowered in plasma with larger isotope mass by means of heavily ion beam probe the core electrostatic potential behavior across the ITB formation is investigated. A transition to a positive electrostatic potential likely leading to positive radial electric field occurs with a lower input power normalized by density in plasmas with heavier ions. This observation is suggestive of the isotope effect in the radial electric field structure information. The self-organized radial electric field criticality having a susceptibility to plasma ion mass can be a mission prize in dissolving the hydrogen isotope effect. Result: experimental setup. Hydrogen isotope effect in the electron ITB is dynamically invested by means of an input power modulation experiment in LHD. In the present experiment, the target plasma is produced by balanced tangential neutral beam.